On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, in Chile, spotted a faint, moving speck that refused to follow a closed orbit around the Sun. Within days, orbital calculations showed this object was on a one-way journey, a hyperbolic trajectory escaping the solar system. It was officially designated 3I Atlas, marking it as the third known interstellar object after 1I Oumuamua in 2017 and 2I Borisov in 2019. Initial estimates put its speed at over 58 kilometers per second, roughly 210,000 kilometers per hour relative to the Sun, fast enough to outrun solar gravity. There was no doubt we had another visitor from the stars in our midst. Astronomers worldwide mobilized rapidly. Telescopes across both hemispheres trained on 3I Atlas as it hurtled inward. NASA's Hubble Space Telescope captured early high-resolution images in July, revealing a fuzzy, teardrop-shaped cocoon of dust surrounding the comet's icy nucleus. The James Webb Space Telescope turned its infrared gaze on the object, while ground observatories from Hawaii to the Canary Islands monitored its brightness. By all appearances, 3I Atlas was a relatively small comet. Hubble data suggested a nucleus diameter on the order of half a kilometer to a few kilometers, wrapped in a growing halo of gas and dust. It was inbound toward the inner solar system on a steep path, due to reach perihelion, its closest point to the Sun, around late October 2025, at about 1.4 astronomical units, just inside Mars's orbit. Then it would swing around and head back into interstellar space, never to return. Humanity had one brief chance to study this cosmic messenger before it vanished. A Hubble Space Telescope image of interstellar comet 3I Atlas, captured on July 21, 2025, showed the comet when it was about 277 million miles from Earth. It appeared as a blue-hued, hazy point with a teardrop-shaped dust coma around its nucleus, trailed by streaks of background stars as the telescope tracked the moving comet during the exposure. From the outset, 3I Atlas piqued interest not just for its origin, but for its behavior. As weeks passed and the comet plunged closer toward the Sun, observers noticed something odd. Most comets brighten dramatically as they approach the Sun, when solar heat sublimates water ice in their nuclei into jets of gas. But 3I Atlas did not brighten quite like typical long-period comets. Early spectroscopic readings from the James Webb Space Telescope indicated that water, normally the main driver of comet activity, was surprisingly scarce. Instead, the comet's hazy coma appeared dominated by carbon dioxide and other carbon-bearing volatiles, with only a trace of water vapor detected. In fact, JWST found that 3I Atlas was unusually rich in carbon dioxide, with only a small amount of water in its coma. This single chemical clue suggested that 3I Atlas formed in a very different environment than comets here at home. Perhaps it congealed in the frigid outer reaches of another star system, beyond that star's water ice line, where carbon dioxide ice was plentiful. In other words, 3I Atlas was offering a chemical fingerprint of its birthplace, and it did not match the typical composition of comets born in our solar system. By late August and early September, data from observatories kept pouring in. A team led by NASA's Martin Cordiner announced a definitive James Webb detection of carbon dioxide outgassing from 3I Atlas, confirming that carbon dioxide, along with some carbon monoxide and carbonyl sulfide, was streaming off the comet as it warmed. Meanwhile, the European Southern Observatory's Very Large Telescope detected familiar cometary gases like cyanide and even vaporized nickel in the comet's coma. These substances are seen in normal comets as well, meaning that aside from the carbon dioxide abundance, 3I Atlas looked and behaved like a comet, as scientists reassuringly noted. Indeed, NASA held a press conference on November 19, 2025 to show off images from Hubble, Mars orbiters, and more, emphatically confirming that 3I Atlas was a natural comet, not an alien craft, despite rampant online speculation.
A 36-hour observational blackout.
For all the exciting data being gathered, Comet 3I Atlas's most critical moments were yet to come. As it neared the Sun in late September 2025, astronomers anticipated a surge in activity. The comet was expected to vent its most volatile ices and perhaps even fragment or sprout new tails as solar heating peaked. Telescopes around the world carefully scheduled observations during this period to capture any such fireworks. Then, fate intervened. In what can only be described as a perfect storm of bad timing, a temporary observational blackout occurred just as 3I Atlas reached its most revealing phase. In late September, a series of unconnected events left almost every major Western observatory unable to watch the sky for about 36 hours. NASA's Hubble went into a brief hiatus for a scheduled gyroscope alignment. The James Webb Space Telescope had to pause observations during a critical instrument mode switch and cooling procedure. Several flagship ground-based telescopes, including Chile's 8-meter giants, were in the midst of routine maintenance and mirror cleaning. To top it off, the U.S. government entered a shutdown on October 1 that temporarily halted NASA's communications and data analysis work. Each of these actions made sense on its own. Together, they created a global blind spot. Crucially, this downtime coincided with 3I Atlas swooping very close to the Sun's line of sight from Earth. For a brief window, the comet was positioned in the sky only a few degrees from the Sun, in near daylight conditions. From Earth's surface, trying to see the comet then was like trying to spot a faint glow next to a blinding spotlight. Under normal circumstances, space telescopes or specialized solar observatories are needed to monitor a comet in such glare. The joint ESA and NASA SOHO Solar Observatory was one of the few assets that managed to glimpse 3I Atlas during mid-October when it passed through perihelion, catching the comet as a tiny speck in the Sun's corona. But in late September, even SOHO's coverage had gaps. For roughly 36 hours, nearly all eyes went dark just as 3I Atlas likely hit a peak in activity. To astronomers, this was a small disaster. Those missing 36 hours meant a section of the comet's light curve, the record of its brightness over time, would have a gaping hole. Any transient outburst, fragmentation, or unusual behavior during that time could be missed forever. It was a once-in-a-lifetime event that we almost failed to record. As one report later summarized, during that exact window, 3I Atlas crossed a region of the sky perilously close to the Sun's glare. Nothing about the object has changed, and yet everything has. The data still in hand was the same, but the implications, the fear of what might have been missed, cast a long shadow. China's telescopes fill the void. The sky, however, was not silent everywhere during that critical interval. While many Western observatories blinked, a network of telescopes on the other side of the planet kept their gaze steady on 3I Atlas. China's astronomical observatories, some of which sit at very high altitudes on the Tibetan Plateau and in the deserts of Qinghai and Yunnan, remained operational and unconstrained by Western schedules. By a stroke of luck and planning, these observatories had no major shutdowns at the same time. When 3I Atlas entered the Sun's vicinity, it was daytime for American and European facilities, but nighttime in Asia. In those hours, Chinese astronomers seized the opportunity. Multiple medium-sized telescopes in China continued to track the interstellar comet continuously during the 36-hour gap, ensuring the comet was never truly out of watchful eyes. China, in recent years, has invested in a distributed network of telescopes, especially in remote, high-elevation sites known for clear, dry skies. The new Lenghu Observatory in Qinghai Province, at over 4,300 meters elevation, has rapidly become a world-class observation base, hosting dozens of telescopes operated by various Chinese institutions. As of 2025, Lenghu alone housed 45 telescopes across at least 12 scientific institutions. Further west, near the border of Tibet, additional observatories in Ali, also known as Angari, and in Yunnan's mountains contributed to an impressive arsenal of instruments. Though most of these telescopes were moderate in size, typically 1 to 4 meters in aperture, they excelled in automation and all-sky coverage. During the 3I Atlas campaign, Chinese observatories dynamically scheduled their telescopes to follow the comet around the clock. As weather or viewing angles changed, one telescope handed off to another. This robotic coordination ensured an unbroken sequence of images, even while larger observatories elsewhere were momentarily offline. Light from 3I Atlas was captured on cooled CCD detectors in a series of relatively short exposures, typically 30 to 120 seconds each. Because the comet was moving so fast, long exposures would have caused it to blur on the sensor. Chinese teams took many short snapshots and later stacked them digitally to boost the signal-to-noise ratio. Every image was time-stamped with millisecond accuracy via GPS-based clocks and saved in standard FITS format with complete metadata. These files streamed through high-speed fiber networks to data centers in Nanjing and Beijing for safekeeping. Engineers jokingly referred to some of these hardened data servers as servers under ice, since they were kept chilled and backed up by independent power to prevent any data loss in the remote mountain conditions. In short, China's observatories never blinked. They caught everything. When Hubble, JWST, and the major Western facilities resumed observations in early October, they effectively had a lifeline to reconnect with the comet's trajectory. In those 36 critical hours, 3I Atlas had moved well over 1 million kilometers along its path. Thanks to continuous astrometric measurements from Asia, the comet's position and heading were precisely known. Chinese teams promptly shared their tracking data internationally, allowing everyone else to realign their instruments without missing a beat. What could have been a frantic search operation turned into a seamless continuation of science. The results of this unbroken monitoring were remarkable. During the roughly day-and-a-half window that Western observers missed, 3I Atlas underwent noticeable changes. Chinese telescopes recorded the comet's brightness increasing by roughly 0.3 to 0.4 magnitude, indicating a spike in outgassing activity. In the same period, the comet's coma developed an elongated feature toward the sun, essentially a sunward-pointing jet or antitail of dust. Such features are unusual and suggested that the dust properties of 3I Atlas were indeed atypical, with grain sizes differing from local comets. Thanks to the vigilance of Asian observatories, humanity did not miss this moment. Collaboration and confirmation. Once 3I Atlas rounded the sun and emerged from solar glare by late October, telescopes all over the world trained on it again. With a continuous data set in hand, researchers combined Chinese observations with those from Hubble, JWST, and others into a comprehensive analysis. The verdict was clear. Astrometric calculations pinned 3I Atlas's eccentricity at about 0.14, confirming beyond doubt that it originated outside our solar system. The combined orbit solution achieved positional accuracy on the order of 0.2 arcseconds. Composition findings solidified as well. The comet's coma was rich in carbon dioxide and relatively poor in water compared to known comets. The dust grain analysis indicated larger, heavier particles, consistent with the anti-tail phenomenon observed. Together, these details painted a coherent picture of 3I Atlas as a small interstellar comet that likely formed in the cold outer zones of a distant protoplanetary disk billions of years ago. Chinese astronomers formally presented their findings in a report from Beijing. The announcement concluded with a striking line: "Nothing about the object has changed, and yet everything has." A new balance in astronomy. The saga of 3I Atlas highlighted an uncomfortable truth. While most of the world's largest telescopes are operated by Western institutions, a distributed network of smaller telescopes proved more resilient. In this case, persistence mattered more than size. A coordinated grid of modest instruments ensured continuous coverage when the biggest facilities could not. This was not the end of large telescopes, but a demonstration of complementary power. The event became a case study in global cooperation, showing that science advances when observers fill in each other's blind spots. In September 2025, it turned out the right place at the right time was China. Epilogue. Everything has changed. After perihelion, 3I Atlas faded as it departed the inner solar system. By December 2025, it passed its closest point to Earth, nearly 270 million kilometers away, and continued outward into interstellar darkness. But its brief visit left a lasting impact. 3I Atlas became the best characterized interstellar object to date. We confirmed it was a natural comet, learned about its alien chemistry, and witnessed behavior both familiar and strange. More importantly, we learned something about ourselves. The observation of 3I Atlas showed that modern astronomy is no longer owned by a single region or set of institutions. It is global, distributed, and resilient. For 36 hours, half the world accidentally looked away. The other half did not. And in that narrow window, an interstellar messenger whispered its story into the record. Unseen but not unheard, a fragment of another sun passing quietly through ours.